Do you know where the test is going to be?
Do I know where you're? Oh, yeah, it's going to be in the labs. So, you guys, have you done that? Have you just taken the exams in here? The labs on either side. So where you have Orgo lab, and then on the other side of the hall is the Gen Chem lab. I have those reserved.
So we're just like split up half.
Yeah, I need to find out. It may well be that we can all go into organic lab. There's I think 20 of you. No, there won't be that many. Quite a few of you are. I bet we all fit in the organic lab. So come to the organic lab unless you're here. My other section has too many to go in that section. I think you guys fit. I also got to go through and figure out how many are quarantined, because it's not a small number at this point. Yep.
For the test, is the amount of Chapter 7 content going to be like
Same.
equal to all the other ones? Okay.
Yeah. 7, 8, 9, and just a hair of 10. Right, so yeah, Chapter 7, Chapter 8, Chapter 9, pretty much all. I looked, I think there's one reaction. All right, so what's the product of that? Go ahead and draw the product of that. I actually am going to talk about something else here in a minute, but.
Do you have to have NaHSO3 for a nosmolysis? Or not a nosmolysis?
Yeah, so if you guys need to use that in a synthesis, okay, so if you were using this reaction in a synthesis, if all you write is osmium tetroxide, I'm fine. But if I write it, I'm going to put up all the stuff you'd see. So this is going to be a syn dihydroxylation. OHs on both of those carbons. I think, change color just because I don't get to do that much more. I think they use this reagent, KMNO4, and I think some other stuff. I think the book has that as an alternative reagent to do a syn dihydroxylation. And I didn't cover it. So I'm not going to ask you what potassium permanganate does. But if you've learned it and you need to use it on a synthesis, that'd be fine. I think that's the only reaction in Chapter 8. I said you don't have to know. Potassium permanganate is so osmium tetroxide I mentioned in class is a really toxic, very expensive reagent. Potassium permanganate is a lot easier to come by, and it's way less toxic. But it's also a more powerful oxidant. So doing this basically the reason I eliminate it is it usually over-oxidizes things. So while it may be possible to do that reaction, it also it'll oxidize this. These will both become carbonyls and break carbon-carbon bonds. It's pretty rough. None of that you need to know, but I like to tell you. Okay, so yeah, 7, 8, 9, and 10, it's either an email or a Canvas announcement where I sort of tell you what mechanisms in 8 and 9 you don't have to know. Really, the mechanisms you need to focus on are Lewis acid base. Something has electrons, points a curved arrow, and something that doesn't have electrons, stuff happens. Okay, so today, I think I'll start this in the middle. How would we do this? Imagine that you took these 3 alkenes. So I've only drawn one arrow there with HCl, but you're going to use HCl on all of them. You're going to use the 3 alkenes, add HCl across those double bonds. So draw the product you would get, and then rank the reactions. Which one of these reactions is the fastest, and which one of the reactions is the slowest? Sorry, I don't want the formal chart here. All right, so on the I'll do the top one, and then you can see what you think. So, again, this is just electrophilic addition of HCl across a pi bond. Pi bond is going to be a base. It's going to make a bond to the H. That H can't have two bonds, so the HCl bond breaks. And the product we get, well, this goes through an intermediate cation. Right? So you go through the tertiary cation that's more stable than the primary cation, that's your other option. And then chloride attacks the cation. Right, so you put the H on the less substituted carbon, the chloride on the more substituted carbon. That's Markovnikov's rule. Again, don't focus on substitution, focus on the cation. Reactions that go through an electrophilic addition like this, that go through a carbocation, are always going to go through the most stable cation. Yes?
Do we have to, when we're drawing the mechanism for this, do we draw the intermediate as well?
For a mechanism has to have every intermediate.
Okay. So
Yes.
I wouldn't just draw the arrows and then draw the product or draw.
Right, so I mean, I've seen this before where people will do, I'm trying to imagine what you could do here. So you might have something like this. And I mean, I get this. Sorry, that's the wrong way. Let me violate Markovnikov's rule while I'm trying to teach you. Right, like do something like that. Like those two arrows, or even you might even add this in. Like those three arrows are the mechanism. But if you put them in one step, what you mean is this all happens at the same time. All right, so you have to sort of block out what happens when. So the mechanism I drew, I'm saying the bond from the carbon to the H is formed at the same time as the HCl bond breaks. And then you get something. And that intermediate is not going to live very long. Like cations are really reactive. But it's there for a fleeting instant. And then the chloride attacks. So you like a properly drawn mechanism has to have every intermediate. And that's a pretty common mistake I see people make, is just piling on arrows onto one molecule. And you shouldn't memorize this, but as a general rule, if you find yourself drawing a mechanism and you've got like 4 or 5 or 6 arrows on one intermediate, you've probably done something wrong. And I mean, that's, like I get on an exam, you might know you've done something wrong, but not know how to do the right one. Like mechanisms are really tough. You can't guess a mechanism. And that's why I don't think I convince people, but I really am not ever laughing at students. I see crazy mechanisms and sort of I don't know, it's entertaining as an organic instructor, right? Like, but I'm not, like if you either don't know it or you get confused on it, right? right? It's not like, if you see 2 plus 2, it's got to be a number, right? Like you know a math problem is going to be a number. A mechanism, once you go off the rails, it's probably going to be really badly wrong. So don't sweat that. Just try to keep in mind that the arrow is always going to start with electrons, go to something positive. H is never going to have 2 bonds. Carbon, nitrogen, oxygen, never going to have 10 electrons. And then, like I said, this other one, you're usually not going to have a ton of arrows all together. Sometimes you will. That's not like a rule of the universe. But if you look at the basic mechanisms in chapters 7 and 8, like E2 has 3, I think. SN2 is 2. Electrophilic addition is 2. Like most of them are 2 or 3. Okay, so if you put the chloride on the more substituted carbon, I'm not going to draw the mechanism, I'll just draw the intermediate. All right, so you get that. All right. So those would be your products. Now that I've drawn out the intermediates, take a look at what you thought would happen with the reaction rates. Like which one was fastest, which one was slowest, and see if you're still happy with that. All right, so which reaction do you think is fastest?
Middle reaction.
Gotta vote for the middle. Yeah.
I think this is probably wrong, but just my natural assumption is that it would be the one with the nitrogen, the one on the bottom.
Why? What's special about nitrogen?
Because it's got more resonance to it.
So if the nitrogen were neutral, you'd be right. All right. So there is resonance here, and the reason that's wrong is that. All right, we've got 2 positive atoms bonded to each other, and that's going to. You would like to have all the atoms be formally neutral. But if you can't do that, you want opposite charges close to each other, like a plus bonded to an atom that's minus. The charges can sort of neutralize each other. Having atoms that are formally positive bonded to each other is really destabilizing. So the bottom one is the slowest reaction. And you can actually draw a resonance structure here that's really bad. Again, you wind up with a plus nitrogen bonded to a plus O. That plus O is not just a normal plus O. You'll see this in a minute. But this O here, this positive oxygen, doesn't have a full octet. All right? In general, anytime we don't have an atom with a full octet, that's bad. Having an electronegative element like oxygen not have a full octet is way worse than having a carbon not have a full octet. All right? So this is a really bad resonance structure. And in fact, this bottom reaction wouldn't happen. With that nitro group, this doesn't happen. If the nitrogen had a lone pair, this would be really fast. And you see that on the one in the middle. Right? So the oxygen here has a lone pair. It's got a lone pair here too. It's got 2 lone pairs. And so you can get a resonance structure. I'm running out of room. All right, so you get a resonance structure there. So that positive charge is delocalized. And it would be really easy. In fact, probably I see some looks. You're like, wait, just on the bottom you said positive O is bad, and now I draw a positive O, and I'm like, look at this. This is such a good resonance structure. The difference is, on the bottom, this positive oxygen doesn't have a full octet. Right? So not only is it formally positive, it actually doesn't have enough electrons. This green resonance structure, the oxygen's also positive. It has a formal positive charge, but the oxygen has a full octet. So it's got as many electrons as it can have, and it's just kind of loaning them out to the carbon next to it that doesn't have enough electrons, right? This carbon doesn't have a full octet. By the lone pair on oxygen interacting with that positive carbon, all the atoms end up with a full octet, right? So that positive charge is really, truly delocalized. So the middle reaction is the fastest. There's another way to look at this. All right, so you can sort of judge these reactions by how stable the intermediate cation is. Oh, so I want to finish up. I'm sorry. So your sort of instinct about nitrogen, like a lot of nitrogens you guys see, a neutral nitrogen is going to have a lone pair, and it does this even better than oxygen. Right? Nitrogen's going to share its electrons better than oxygen because it's less electronegative. All right, so trying to judge these reactions, there's another way to look at this. And that is by looking at how electron-rich the alkene itself is. So if you look at the mechanism, the alkene is giving away electrons. It's a base. So the more electron density in the two carbons making up the alkene, the better base it's going to be. So if we draw a resonance structure for the starting nitroalkene, we can take the pi electrons in the alkene and push them out onto the oxygen. Remember, when you draw a resonance structure, that your overall charge has to stay the same. I tripped myself up there because I had gone from a neutral molecule to a negative one. I can't do that. All right, so if you see the arrows to draw this resonance structure, right, the electrons are flowing away from the alkene. So the effect of that nitro group is to pull the pi electrons away from those two carbons. That's going to make those two carbons less likely to be a base. On the top one, on the other hand, the lone pair in the oxygen pushes electrons into that pi bond. So you end up here with that blue resonance structure where the atom that's going to make a bond to the H has a negative charge. So the effect of this methoxy group is to push electron density into the pi bond. That's going to make those two carbon atoms more nucleophilic, more basic. So we can then classify groups, substituents on pi systems as either being electron donating or electron withdrawing. And we're always going to use that relative to H. Right? A substituent is a substituent because it stands in place for a hydrogen. We're going to call electron withdrawing groups EWGs, electron donating, or sometimes you'll see releasing. These are going to be EDG. Electron donating group, electron withdrawing group. Hang on. All right.
So, I was going to say, why is the middle reaction, why is that resonance structure, why are the electrons in? Is that just because it's close, is that just because the negative is closer to the alkene, or?
I mean, in the starting material, there's significant partial negative charge on that carbon. Right? Because in the resonance structure, there's negative charge there. That's going to make that carbon quite a bit more basic than it would be. And if you look at the reaction, I didn't really show it that way, but the H that gets grabbed goes onto that carbon.
Yeah.
Right? So the atom that's actually grabbing the proton in the middle reaction has significant negative charge, partial negative charge. On the bottom, right, the H actually goes onto an atom that has significant partial positive charge. So you're looking at, a partial negative atom making a bond to H or a partial positive atom making a bond to H. Okay, so you can always figure out if a group is electron donating or withdrawing by resonance. Right? You can just draw your resonance structures. Like I get at this point, I say that like, oh, that's easy, right? Just draw some resonance structures. This is why we say at the very beginning you need to be able to draw resonance structures. But I appreciate that just because I told you that doesn't necessarily mean that's going to be a really fast process for you. So at a glance, you can actually figure out if a group should be withdrawing or donating. And here is how. So an electron withdrawing group let me get it written down. All right, so for an electron withdrawing group, the atom that is actually bonded to the pi system is either going to have a really strong partial positive charge or a full-on net positive charge. All right, so a nitro group. The atom that's directly bonded to the pi bond is positive. Makes sense then if positive atoms are going to pull electrons toward themselves. But you can also see this in carbonyls. So in the carbon-oxygen double bond, that carbon has a really significant partial positive charge. And that's the atom that is bonded to the pi bond. All right, so this is the key thing here. When you're judging is this group electron withdrawing or donating, you don't really want to look at the entire group. You want to look at the atom that is directly attached to the pi bond. Right? Resonance, for resonance to happen between two groups, they have to be bonded to each other. And there's a few more. So even if you had something like this, right, there's some partial positive charge, but there's not as much partial positive on that CH2OH, the sigma bonded CO, as there is on the carbonyl. And so I didn't mean to necessarily, but I've sort of written these. The stronger electron withdrawing group is this nitro group, then you work your way over to a weaker, right? I'll let you finish writing. I feel like I'm going fast. Yeah.
So I understand like the definition and such, but how does it make it slower by being electron withdrawing? Like how does it make the reaction?
So you can't just say it makes a reaction slower. It's what reaction it is. So in this mechanism, all right, so in the reaction here, okay, so I've drawn the resonance in blue. I'm going to draw the mechanism arrows in red. Right? So the reaction to happen there, the pi electrons are being abased. But competing with that is this nitro group. Like it's pulling on these electrons. Like if you put it in human terms, I don't know if I can do that. I like to think about this in like financial terms. If you think about the electrons basically being money. So none of you are married, so this doesn't work so well. But like, let's say you've got a competing monthly, you've got a credit card, you've got debt, you've got student loan debt, right? This nitro group is a loan, a deep debt you have. You have to pay these people X amount of dollars every month, or they break your knees. Right? That's a nitro group. Your buddy comes along and needs you to buy him dinner. You're less able to do that, right? So maybe you still can, but if I've got a $500 student loan payment tomorrow, and you come to me and want a $100 dinner, On the donating group, again, the mechanism is the same. So this pi bond is going to make a bond to the H. The electrons are going to be released from the alkene to the H. But now instead of having a debt, I don't know, you have a rental house, right? You've got some rental property that pays you $1,000 a month. Check's coming in tomorrow, your buddy rolls into town and wants to go eat a steak, you go eat a steak. Like, that's a really easy choice. All right, so, yeah, so it's just, you want these arrows sort of reinforcing. Again, it's like a current. So essentially, by having the atom with the lone pair bonded to the pi bond, you're essentially giving the pi bond access to these electrons. Right? So that makes, we would say that this alkene is more electron rich. We would say on the nitroalkene is electron poor. And again, that doesn't mean the nitroalkene will always react slower. It means in this reaction, where the pi bond is being a base, the nitroalkene will react slowly. If you had a reaction where a nucleophile was going to attack the carbonyl, or sorry, not the carbonyl, if the nucleophile was going to attack the alkene, right, so electrons are coming into the alkene, now the nitro is going to react faster because that nitro can absorb that. The methoxy is crowding it with electrons.
So then for E donating, would that be partial negative or negative?
Yeah, so for an electron donating group, so this is for the strong ones. Right, so the atom directly bonded to the alkene is going to have a lone pair. So the lone pair, you know, you might think, so it could be this. This would be super strong, right? You have an O minus bonded. So now it's not just that you have a lone pair. You've got a negative charge, right? That oxygen's got a ton of electrons. That's really a special case. That's a super strong base. You're not going to see it a lot. More commonly, what you would see is just a neutral oxygen like we put, like I drew over there. Or you might see a nitrogen. So again, this is sort of what you were saying, Marty. If you had a neutral nitrogen there with a lone pair, that lone pair is going to be in resonance with the double bond. Sulfur, etc. On the other hand, we also have weak electron donors. And this would be any alkyl group. Right? This goes by hyperconjugation. We talked about hyperconjugation back when we did cations. So when we talked about cations, a tertiary cation is going to be more stable than a secondary, which is more stable than a primary, which is more stable than a methyl group.